spare iron stores and cause no iron deficiency. And this was shown by our colleagues, the hematologists doing iron chelation for thalassemia. So there was a body of evidence that this is a harmless compound available over the counter and largely used because I think something like 15,000 children are given this compound worldwide. So, of course, before launching a clinical trial, we have to devise a preclinical study, of course. And this preclinical study has been done by Joachim Munnich in Jerusalem. And the principle is such, it's a relatively simple one. Calcium green is a fluorescein analog, which undergoes fluorescence quenching by iron and dequenching when iron is scavenged by a chelate. So you are playing with the quenching and dequenching of the fluorescence of calcium green. So the question was whether Deferiprone could stop the quenching and trigger the fast recovery of fluorescence. And can this fluorescence be applied to cell compartment to estimate iron content within the particular subcellular compartments? Here is again the principle. Here is the calcium green. When calcium green see iron, it quenches and the fluorescence extinguishes, disappears. And instead of green, you will see white. No more green. Now, if you chelate iron by deferoxamine or deferiprone or whatever the iron chelator, you will restore the fluorescence by dequenching. So you have to play with the dye. And here is another representation of the same principle. Here you have a nice fluorescence. You add iron, you quench the fluorescence, you add a chelator, deferiprone, and you dequench the fluorescence, which reappears. So this is the principle. And here you can see some preclinical studies done in your laboratory, and you see the nice green color due to calcium green. And in the next slide, as a function of time, you will see the extension of the green fluorescence by iron, and you will see slowly after 20 minutes that the iron is quenching the fluorescence, extinguishes the green color, while iron causes an oxidative stress into the mitochondria, shown by the rhodamine on the lower part of the slide. So now, another question is whether we can target the compound and to particular compartment. And the answer is yes. Yes, we can bound the probe to particular peptide, and we can target particular compartment, the mitochondrion, the nucleus, the lysosome, and so we have the tools to follow the fluorescence in various compartments in the presence of iron. So he had, because this is done by Joao mostly, he has the tools. So he can really target the probe and the fluorescence to particular compartments of the cell, the nucleus, the mitochondria, the lysosome, based on specific sequences. No time. Now you see a nice picture where rat cardiomyocytes are being loaded selectively with FMS calcine, and for this reason the calcine goes to the mitochondria, and then you have had iron, and so you have an extinction of the fluorescence. And then you had Deferiprone, the chelator, and you see very nicely that the fluorescence reappears, because you have dequenched, the quenching, and you have removed iron. And this is clearly shown by the reappearance of the fluorescence. And not only that, but you can also play with that from one compartment to the other. You can send the iron into the, you can displace the iron from one compartment to the other. For instance, you can send iron bound to calcium green to the nucleus, using a specific target, the keystone. Then this it quenches the fluorescence, and if you add Deferiprone, you will dequench the fluorescence into the nucleus and remove iron from the nucleus to another compartment. And you can see, for instance, the trafficking of iron from one compartment to the other when given Deferiprone. Very nice, very funny, and this is shown on this picture. Here you can see that the nucleus is extinguished completely before Deferiprone, and you can see that the green fluorescence is very low, and then you add Deferiprone, you remove quickly the iron, you dequench, reappearance of the fluorescence, and then you see that the iron went to the mitochondria where it triggers an oxidative stress. So clearly we had the clinical, the preclinical evidence that this compound is available, it's not harmful, it's reasonable, there is a rationale for that, and this we have discussed for long with Pierrot years ago. But what we liked, in fact, was a available compound, and this compound was available. So we have launched a first trial, which was an open trial, on a small number of children. So the bias, of course, now I'm very unhappy about that, because it was not smart to start with a open trial. We should have started with a double-blind trial immediately. But this was the first step, done in a dozen of children, boys and girls, given independent for more than 2 years, with a nice answer to response to Devenon as far as heart involvement is concerned. No other antioxidant was given. Deferiprone was given orally, and we launched a trial for 6 to 12 months. And the principal endpoint was the T2 star. We had no particular clinical goal at that point. We were only following the decrease of iron based on the T2 star technology. And of course we followed the patient clinically, and also we followed the blood test very closely. And you can see that all children had a nice decrease of iron accumulation very quickly. Early on, after 2 months, really the iron has decreased markedly in all children. And this is the individual curves. And this is an interesting plot that is very familiar to hematologists, and they knew that for long. This slide shows that the higher the iron accumulation at onset of the trial, the higher the extraction. When you start high, you extract much. When you start from low iron accumulation, you don't extract that much. So the higher the iron overload at onset, the higher the extraction.